Thank you so much, Lisa, for the very kind introduction. Please chime in if you cannot hear me or if the slides are not visible, and otherwise I'll get started. So it is a pleasure to provide the seminar to this group and to see a lot of friendly faces that I've had the opportunity to meet before. And today I'll share some of the work focusing on environmental justice, climate, air pollution, and key decisions for the US electricity sector. And so a little bit about the broad scope of the research that we pursue in my group. We're really passionate about looking at sustainable energy systems and thinking about the engineering and economic feasibility of low carbon, sustainable, affordable, and socially just energy systems via both the efficient provision of energy systems as well as the supply of energy. And of course, as we think about the future of energy systems, we have to do this in a policy context. So a second stream of research has to do with understanding about how to design effective energy and climate change policies, as well as to understand whether ongoing policies are achieving the intended goals and do not have unintended consequences that need to be addressed and mitigated. And finally, we're doing all of these decisions in the context where we have people that have behaviors that make decisions. So a third stream of research has to do with how do people make decisions and how do they behave, and how does that affect and shape the formulation of our energy system. And finally, the emphasis of much of the ongoing work over the last couple of years, as well as the focus of the future work, is on quantifying distributional and environmental justice effects associated with decisions in energy systems. This is thanks to a phenomenal group of graduate students at Stanford, as well as still ongoing collaborations at Carnegie Mellon University, where I was previously, ranging from students that are in the Energy Resources Engineering program, in the EASIUR interdisciplinary program, also at Stanford, management science and engineering, mechanical engineering, civil environmental engineering, just to name a few. Now, to this crowd, this is not going to come as a surprise. We need energy. We benefit enormously from all the energy services that we have provided, but the benefits that we have from having all these energy services are also associated with externalities and costs that are not traditionally monetized and include in the way the markets operate. And so those entail costs associated with climate change impacts and also health damages from air pollution. And much of this talk has to do with the fact that these two streams of impacts and externalities have traditionally been tackled in isolation, but there are really key linkages in the way we think and plan future energy systems that have implications for both, and where the consequences and outcomes can be vastly different if we're thinking just about climate change or air pollution. So if we think about energy systems, and in particular in electricity generation, we'll have the fuel extraction and transport. And then at the power plant, we'll have two key streams of pollutants. So we'll have greenhouse gases such as CO2 and methane. And those are global in their nature, having a global dispersion and staying for a very long time in the atmosphere. And at the same time, you have the emissions of a very different type of pollutants, so health damaging criteria pollutants like SO2, NOx, and PM. And those will result from both the direct emissions from the combustion of fossil fuels called primary PM, as well as the formation of secondary PM that results from the emissions of SO2, NOx, that will react with the ammonia present in the atmosphere to form this secondary PM. And so this concentration of PM, is it something that we're worried about? And the answer may be, it depends. If the emission occurs and leads to an increasing concentration in the middle of nowhere and where it's small enough that it may not have large ecosystem damaging impacts, perhaps not. But if those emissions result in an increase in concentration in densely populated areas, then we'll have an effect in terms of premature mortality. So population density matters, the location and dispersion of the pollutant matters. And so this is a more localized effect, but where still the dispersion of those pollutants may cross state boundaries, as we'll see in the next few slides. So PM 2.5 is associated with increased mortality rates from cardiovascular diseases, chronic obstructive pulmonary disease, and lung cancer. And so where the emissions occur and where the concentration increases and the amount of people that are impacted by such concentration increase will matter. And so these two streams of pollutants, GHGs and criteria pollutants, do have tremendously different implications considering the of the importance. Not only that, but the type of emission source also matters. So, for an example, we have power plants that may have emissions primarily of SO2 and NOx, which will have a very wide dispersion. Then we may have industrial facilities that will produce emissions of SO2 and other hazardous air pollutants, which will have a medium to wide dispersion. And then trucks and vehicles, which are going to produce emissions at the ground level and will emit primarily NOx and particulate matter direct emissions, as well as VOCs. I'll pause just to ask if you're hearing me okay, as I just have a message popping up on the screen saying that my internet is unstable.
You seem to be back to regular right now.
Okay, just let me know. Thank you. So the first piece that I'll talk about is this issue about how the distributional, what are the distributional effects associated with air pollution from electricity production. And so I was very fortunate to collaborate with three exceptional researchers for this piece, Meneder Ting, Chris Tessem, and Julian Marshall. And we really wanted to get at the issue of how is air pollution distributed and its consequences, meaning are we all breathing the same air? And so under the lenses of environmental justice and zooming out for the importance of PM 2.5 in a broader context, fine particulate matter is the largest environmental health risk in the US and globally. In the US alone, it still accounts for more than 100,000 fatalities per year. And the electricity generation is still a significant contributor to air pollution and predominantly due to the emissions from coal power plants. Even if such contribution has declined over time, and that's thanks to environmental regulations that have imposed the air pollution control technologies in the stack of power plants, as well as a transition from coal to natural gas, which was mostly driven by cheap natural gas. And finally, to a lesser extent, also the increase in renewables that we see in the grid in some regions. When you look at the electricity sector alone, the existing estimates from PM 2.5 related mortality range from 10,000 to 52,000 premature deaths per year. And this is depending on the year, the type of model being used, and so on. But one of the things we've noticed is that the demographic distribution of that resulting exposure was up until now largely unknown. And so we estimated the exposure to and health impacts of PM 2.5 from electricity generation in the US. And we did so also for each of the 7 regional transmission organizations or RTOs for each US state and from and to a state by income and race. So a little bit about the modeling approach. We tackle this problem using an integrated assessment model and actually relying on the use of integrated assessment models that have been developed by the co-authors of this study. And so how do this work? Well, first and foremost, we rely on emissions inventories that have detailed annual emissions from all point and area sources to establish a baseline on both the emissions inventory and to run the model one first instance to understand the baseline concentration of PM that results from all sources of emissions. Once we establish that baseline and the underlying PM concentration, we do a perturbation from one emission source at the time. So for each power plant, we incrementally increase 1 ton of a specific type of pollutant and understand the implications of such for the increase of PM 2.5 concentration across the entire United States. And by computing the difference between the resultant concentration with that perturbation and the baseline, we have an attributed increase in PM 2.5 concentration due to the emissions of a specific source and location. Then in a second step, we want to understand not only the increases in concentration, but the implications for that for premature mortality. So we use a dose response function that associates the increase in concentration to premature mortality. We use the ACS dose response function, which is the state-of-art function currently used in these types of assessments. In the sensitivity analysis, we also use alternate dose response functions and assess their implications. And we couple this information with census level data at the block group on household demographics, including income and race and ethnicity, to understand the overall implications by demographics too. So I'll jump a little bit to the key overarching results. We find that 16,700 premature deaths are attributable to electricity generation nationally. And so if we average that across the service provided by electricity generation per terawatt hour, this amounts to roughly 4 premature deaths per terawatt hour of electricity generated. And we find that 85% of premature mortality is attributable to EGUs that are within the scope of an RTO. And of these total estimated premature deaths from electricity, 90% of such are due to coal electricity generating units. A little bit more about mapping out what are the RTO's boundaries and their electricity generation mix composition. So on the right, we have the different RTO regions colored with different colors, and as well as the share of coal in their electricity generation mix. And to the left, we have a table that summarizes some of the findings and characteristics from these regions. So we see that regions such as MISO, which is shown in the map as dark blue, and PJM, which is shown as navy blue, are very large regions providing the largest amount of generation. And given their share of coal in the overall electricity mix, are also amongst the largest in terms of premature deaths per terawatt hour, as well as absolute number of premature deaths due to electricity generation. And then we have other cases like SPP, which is this olive green region, which are smaller markets, but have a very large also intensity in terms of premature deaths per terawatt hour generated, as well as a very large number of total deaths given the very large share of coal generation. So this sort of magnitude of attributable premature deaths across the electricity sector was updated, but there was a range, as I mentioned previously in the literature, from 10,000 to sort of 52,000 premature deaths. So the next layer was really what are the sort of damages for different demographics. And so moving to the next slide and walking you through the axis first, the vertical axis shows the premature deaths per 100,000 people associated with electricity generating units PM 2.5 emissions. The horizontal axis shows race and ethnicity groups as folks self-reported in the census. And so first we see that across the US and on average, air pollution associated with electricity generation entails an average of 5 premature deaths per 100,000 people. And now, when we look at this across race and ethnicity, we see that Black African American have highest exposure and rate of premature deaths when contrasting to other groups, followed by white non-Latino. So the second question is, how does it differ by income? And let's look first at income segments alone and on average across the United States and how things differ by different race and ethnicity groups. So on the vertical axis, we have premature mortality per 100,000 people, again, the same thing. On the horizontal axis, we're showing US household income groups in $1,000. And so we see that as income increase, we have a slight decline in the premature mortality exposure associated with electricity generation, meaning higher income households are generally located in places where they are breathing cleaner air. Now, when we show the same figure, but now by race and ethnicity, we do see that across all income segments, Black African American are more exposed to air pollution than the other groups, followed by white non-Latino. And the size of the circles correspond to the number of people that are in these different income brackets. So that's one lenses of distributional effects. The next one that I would like to talk about is where are the damages created and who suffers the damages? Meaning, how much of the damage to air pollution from electricity generation is sort of self-imposed by emissions in the state versus coming from elsewhere. And so we'll break this down in a panel of maps, and this is the first one. So in this first one, I'm showing the total premature mortality in each state from total PM2.5 electricity generated emissions across the entire US. So this is really premature mortality that occurs between state boundaries, regardless of where the pollution originates. And we see states like Pennsylvania, Texas, and Ohio, where we have very high numbers for premature mortality that occur between the state boundaries. And so the question is this due to the electricity mix that those states have, or is the pollution coming from somewhere else? So breaking this down, the second panel shows the damage to self, meaning the premature mortality inside each state boundaries that is associated with emissions that occur also between state boundaries. And highlighting again Ohio and Pennsylvania, you see that the numbers are much smaller than what we saw in panel A, meaning that there is, and some for Pennsylvania is still large, for example, but the premature mortality that occurs to the state in the state boundaries that is due to emissions in that state is much smaller. So part of the damage will come from neighboring states. Now let's see the damage to others. So this panel corresponds to the premature mortality that occurs outside of the state due to emissions that occur between state boundaries. And again, looking at some of the states, we see that Ohio and Pennsylvania are imposing very large health damages from electricity generation. They just occur outside of their state boundaries. And finally, in this last panel, we show the net effect across emissions. So this corresponds to the self-imposed damages plus the damages to others minus the damages in the state. So large negative values indicate situations where you have a lot of premature mortality between your state boundaries while not contributing to the overall emissions and premature mortality in other states. And you see locations like New York, where it has the largest amount of net damages that are imposed on the state while not contributing at all to emissions, to damages to others, as we can see both in panel C, or damages to self, as shown in panel B. So some of the key findings are that average exposures are the highest for Black African American people, followed by non-Latino white people, and exposures for the remaining groups are somehow lower. We observe that disparities by race and ethnicity are observed across each income category, indicating that the racial and ethnic differences in exposure hold even after accounting for differences in income. And so this is really due to the way we've organized our cities and urbanization and where houses are located. And more work is needed to understand the specific relationship between those aspects, but we hope that this work provides a first starting point to explore this sort of issues. We see levels of disparity that differ by state and income, so depending on both the electricity mix that the state has as well as its specific demographics. So in the SI for this paper, we show similar figures to what I've shown here, but for each different state and RTO. And we find that the exposures are higher for lower income than for higher income, but that the disparities are larger by race than by income. And geographically, we observe large differences between where electricity is generated and where people experience the resulting PM2.5 health consequences, with some states being net exporters of health impacts, whereas others are net importers. And for 36 states, most of the health impacts are attributable to emissions in other states. And most of the impacts are attributable to coal rather than other fuels. I would like to move on to another piece that is related to the first one, but where we bring in climate change too as part of the decisions. And specifically, we're thinking about optimizing the emissions and damages reductions from the US power sector when considering both climate and health benefits. So this paper was published with Brian Sergey, who is a former PhD student of mine that is now a researcher with NREL, and several faculty members across different institutions, Peter Adams, Nick Miller, Alan Robinson, Steve Davis, and Julian Marshall. And these co-authors have been developers of reduced complexity models for air quality. And here we actually use and contrast the results of those three models too, to understand the implications of such for the decisions on climate and health. So first, regarding the broad context and relevance, as I mentioned in the beginning of the talk, climate policies often treat improvements in air quality and health as co-benefits from the climate policy. So that was the case even in the accounting from the Clean Power Plan. Despite the linkages between health and climate, there are few policies that have been explicitly designed to optimize for improvements across both dimensions, and the choice of which power plants are replaced by low emissions alternatives can dramatically alter the health benefits from a given reduction in system-wide emissions. So there has been some previous work, but there has been limited exploration of how spatially granular co-optimization of climate and health could affect emissions across US power plants. So we did that. So a little bit about the modeling approach. So we've explored the optimal locations for emissions reductions using an integrated treatment of climate and health benefits. We do so at the county level. We've developed a capacity retirement and expansion model to explore the implications of location when integrating climate and health considerations in emissions reductions. And we use this tool to determine the optimal investment in generating capacity given a set of objectives and constraints. And we used the model to simulate a policy that would aim at reducing CO2 emissions by 30% across the United States, while minimizing social costs, and comparing those scenarios when including climate damages only, or including also explicitly health damages from air pollution in the objective function. We make several simplifying assumptions. An important one is that we assume capacity needs to be built in the same county where a plant is being replaced, thus eliminating the need for additional transmission infrastructure. And although this may abstract from real siting decisions, it provides an initial insight on how health benefits may change depending on the design of the policy. A little bit on data and assumptions. First, we need a good characterization of the existing fleet. So for that, we use the 2017 EPA's Continuous Emission Monitoring System, SEMS data, which includes both emissions and generation for all fossil fuel units larger than 25 megawatts. And we have description of unit level data on annual emissions for CO2, SO2, NOx, as well as the generation, the fuel and unit type, the facility location, including the coordinates of the facility. And then for the implications on changes of greenhouse gas emissions and their damages, for CO2, we assume a social cost of carbon of $40 per metric ton of CO2 in 2017 dollars. And then in a sensitivity analysis, we use a wide range of social cost of carbon values to understand the implications of that assumption. And we also consider the climate impacts associated with methane leakage from the use of natural gas upstream. And so to estimate the methane leakage, we use approximate heat rate assumptions based on NREL-ATB database to back calculate the amount of natural gas consumed at all current or newly built plants. We assume a 3% leakage rate, and again, use a sensitivity analysis on those results, and estimate the total methane release and convert it to CO2 equivalent using a 100-year global warming potential. The methane leakage is not included in the objective function, is just tracked separately as a consequence of those decisions, given that likely policies aimed at reducing emissions from power plants will not include those upstream emissions when considering whether a power plant is meeting a target. And then for air pollutants, we use the inventory of emissions also from SEMS. And then to understand the damages from those air pollutants, we use the same sort of strategy that I described previously for the first paper, with a couple of explicit changes that you'll see in the results. The first one is to contrast the two concentration response functions across all of the results. And the second one is that we use three integrated assessment models and compare the results of such. And so those are InMAP, EASIUR, and AP2. Just one slide about those models, which have been developed by my colleagues. Each of them has a different way to approaching the modeling and of these pollutants. So AP3 uses a Gaussian plume modeling and fairly rudimentary chemistry. EASIUR is a regression-based approximation of a full chemical transport model, and InMAP has a modeling structure more similar to a CTM, but simplified temporally and in terms of chemistry and physics. And so, although all these reduced form models are less precise than the full-scale CTMs for assessing air quality impacts, previous work has found that they exhibit comparable performance to more complex models in estimating annual average PM concentrations from emissions and health damages, and they provide much more flexibility in terms of running sensitivity analysis, and so we do rely on such. What do we assume about the new complexity? So we have two pieces of the puzzle, the characterization of the current fleet, the implications on impacts from climate change and air pollution. And now, what are we going to replace the technology, the existing infrastructure with? So we limit the alternatives for new infrastructure to be either natural gas combined cycle plants, wind, or utility scale solar. And a little bit about the assumptions here on the natural gas combined cycle plants. One of the benefits of using them as a strategy is that high efficiency NGCC plants will emit on-site half of the CO2 and far less SO2 and NOx than coal, thus resulting in fewer health consequences. We assume that the NGCC plants are dispatchable and can meet the same loads as the thermal loads that they are replacing. We assume that emissions rates for replacement NGCC capacity are similar to the generation weighted average emission rates for all NGCC units in SEMS that came online since 2010. So we wanted to do something that was comparable to the recent units and not necessarily completely state-of-art low emissions. And so our estimates of the costs of mitigation may be accordingly be higher than what it would be if we were to assume state-of-art plants. And to estimate the required plant capacity to meet reductions in annual generation by coal, we assume a capacity factor of 56% and the heat rate based on NREL ATB database. And we assume that these plants need to be built in increments of 150 megawatts, which was the median plant size estimate using the EPA needs database. And as I mentioned previously, we also include the upstream impacts from methane leakage in the supply chain, though we don't include it explicitly in the optimization objective function. So that's it for NGCC power plants. And so what do we assume for wind and solar? So for wind, we use site level wind capacity factor estimated from NREL and averaging those values by county. And for solar, we take a similar strategy of using annually average irradiance from NREL's database, which once again, we average at the county level. And we make an important assumption, which is that wind and solar do need to be paired up with storage as a way of providing dispatchable power. So we include the requirement of a co-location of a storage, the lithium-ion battery. And so that makes the combination of wind and wind or solar with storage more costly than otherwise, obviously. But that was, in our perspective, an important requirement to make sure that these plants were indeed available as a replacement for the existing coal power plants. How do we compute the costs of mitigation? Well, we define the total annual mitigation costs as the additional costs from the optimization scenario relative to the baseline. And so this includes annualized capital expenditures from all newly built infrastructure, as well as the costs of operating and maintaining the new plants and fuel costs associated with the new plants in the case they use such. And we also subtract from these costs any reduced O&M and fuel costs from existing coal or natural gas power plants that would stop operating. We use the estimates of capital O&M and fuel costs from NREL, and in the results that you'll see in the next slides, we're assuming a 20-year useful lifetime and a 7% discount rate. Then we did a battery of sensitivity analysis on these two. So we produce a linear optimization model that minimizes the total costs of new infrastructure minus the cost of infrastructure that would stop operating, plus the social cost of carbon times the emissions of CO2 from each plant. And so those are not dependent on the site where the plant is located. And then what we add to this is to explicitly include or exclude from the objective function this marginal damages from a plant and pollutant times the emissions by the plant and the pollutant, and see how that changes our results. So a little bit about results then. On the vertical axis, we're showing the annual damages that we'll have across scenarios. So the annual damages from climate change impacts and from air pollution impacts. And so in the current electricity system, as we have it, the climate change damages when valued at $40 per ton of CO2 would be roughly $70 billion per year. And the damages from air pollution in the system as we have today The estimate will range, again, depending on the air quality model used and the concentration response function. So let's build a little bit on this. In darker blue, we have the ACS dose response function. In the light blue, we have the Harvard 6 cities dose response function assumptions. And the markers, the circle corresponds to the AP3 model, triangle to InMAP, and the square to EASIUR. And so we see that there are differences across models and they are important, but more important than that is indeed the assumption on the concentration response function that nearly doubles the impacts associated with air pollution consequences. So, and what happens when we impose the policy with a 30% emissions reductions and care only about the climate change damages and treat the air pollution consequences as a co-benefit? Well, the policy target is met since it is a constraint, and so the climate change damages get reduced by nearly 30% since we're assuming constant social cost of carbon. And one of the good things is that we see a decrease in health damages that are associated with that policy. So that's really good news. We would have also improvements in air. So the annual health damages would decrease from 34 to 120 billion in the baseline to between 13 and 50 billion per year in the climate only scenario. And so achieving this 30% CO2 emissions reduction policy using a climate only approach also yields the annual health benefits ranging between 21 and 68 billion dollars per year relative to the current baseline in which the emissions are not reduced. Now, what happens when we account explicitly for both health damages from air pollution and climate change damages when imposing the policy constraint? Well, we see that the climate constraint is met and the damages associated with climate change are again reduced by 30%. And we see that by explicitly including the health damages from air pollution, we achieve even larger health damages reductions. So let me just pause. When health is explicitly considered as a co-benefit, the range of annual damages now falls to between $4 and $14 billion. And the annual health benefits increase to between 30 and $104 billion per year when compared to the baseline. So now the economists in the room will ask me also, okay, but how much does this cost and how does that compare to the benefits? So in this third plot, we'll provide the annual benefits in billion dollars. And so I'll pause here also describing the different components of this figure. The C stands for the climate only policy in the objective function. The H plus C as the health damages from air pollution plus climate change damages being both explicitly included in the objective function. We show three sets of modeling estimates for the three different models, so EASIUR, InMAP, and AP3. And the orange bars correspond to the climate change associated benefits from reducing emissions from the baseline. And they are the same across all scenarios given the same assumption and constraint. The blue bars correspond to the health benefits associated with these policies under the different scenarios. The olive green corresponds to the mitigation costs of building the new infrastructure needed to achieve the policy goals under the different sets of objective functions. And the black diamonds correspond to the net benefits associated with pursuing these policies. So these include benefits to health and benefits to climate minus the cost of building this infrastructure. And so a few key messages are that as we include the health damages from air pollution explicitly in the objective function, we do see an increased cost of mitigation by $1 billion to $2 billion per year. But on net, we actually, the benefits that we get in mitigating the health damages from air pollution are larger than that. So we even achieve larger net benefits when incorporating those two things in the objective function for the policy. Now, a few sensitivities to this analysis. Under the baseline assumptions, the model primarily builds new natural gas capacity and a modest amount of wind concentrated primarily in the locations where wind capacity factors are really high. The mitigation costs are sensitive to natural gas prices. So if we assume $10 per MMBTU rather than the original assumption of 3.2, the mitigation costs would increase from 14 to 16 billion to nearly 23 to 27 billion. So natural gas prices are an important component on from this assessment. And in that case, more natural gas starts to be deployed in lieu of expensive natural gas. In these maps, we're showing first in the baseline and then the outcomes of just the climate policy, and finally the explicit climate plus air pollution policy. The circles correspond to the generation from coal that remains under each of the scenarios. And the colors in the map correspond to the annual health damages that are incurred in that location. So those are receptor damages rather than source-based damages. Importantly, when we look at the climate policy and the climate plus air policy, we see that the shutting down or retirement of the coal power plants occurs in different locations if we are assuming one versus another policy. We'll get back to this again in the next few slides to understand the state level implications for these replacements. We also wanted to look at the equity and environmental justice implications to the extent possible associated with these different policy designs. And equity and environmental justice are critical when considering the location of optimal decisions for emissions reductions. And the context is that a policy that optimizes just overall net benefits at the expense of specific groups may not be desirable, particularly if those groups are low income, racial minorities, elderly, or other at-risk populations, which already tend to experience poor air quality and higher health damages from air pollution. And so although our analysis compute county level health damages, and somehow those are coarser than what we would hope for a rigorous environmental justice analysis, we can evaluate how the benefits from different optimization scenarios are distributed across different subgroups using these county level statistics. And so here on the vertical axis, we have the median annual health benefits. And on the horizontal axis, we have the income quantile from the lowest 20% to the highest 20% for different counties. So this is county level distribution of income quantile. The dark blue bars correspond to the health benefits from reduced air pollution when imposing the climate, when considering the climate policy only and treating health damages as co-benefits. The additional light blue bar on top of it is added benefits that are accrued when including both health plus climate related benefits. And so we find that the climate only scenario has a median positive health benefits across all income quantiles, but also that the lowest 60% of the households by income have highest benefits relative to the 20% highest income counties. And so this is associated with the first paper in the sense that the locations with low income were the ones that were the more exposed in the first place. So this is somehow intuitive. Now, this is a similar plot, but where the vertical axis is again the median annual health benefits in dollars per person. But the horizontal axis is now the share of minority in a county population by quantiles. So from the counties that have the lowest amount of minority as part of the county population to the highest one. And so here, in contrast to income, we find that counties with the lowest share of minority are the ones that accrue the most health benefits per person, regardless of the optimization strategy employed. And Ali or Lisa, am I good on time? Do you still have a few minutes to go?
Yeah, you have about 9 minutes.
Great, okay. So the next point would be, where should the new generation capacity be added and where is it needed as the outcomes of these different policies? So here on the vertical axis to the left, we have the new capacity that will need to be installed in our base case assumptions when considering the climate-only damages in the objective function that's in orange, or the health damages from air pollution plus climate damages in blue. In the right side, we have another axis, and this is the share of the state's existing capacity that would need to be replaced to meet the policy goals. And that's shown in the black diamonds across the plot. And so we really see that depending on whether we're considering just the climate mitigation in the objective function plus health and climate, this may lead to very different decisions for a state. So checking, for example, Ohio here in towards the right side of the plot, we see that if the climate only damages are in the objective function, about 12% or so of the capacity existing in the state would need to be replaced. But if we're accounting for health plus climate damages, nearly 50% of the capacity would need to be replaced. So the distributional effects on the costs of implementing such policies are going to be tremendously different depending on the policy design and different across the states too. So we see that Indiana, Kentucky, Ohio, Pennsylvania, Missouri, and West Virginia all replace coal and gas at much higher rates under the health plus climate scenario. And that although some of the greatest changes in capacity are in states where the health benefits are also large, in other cases, substantial coal capacity is replaced in states where the in-state health benefits are modest. It is the out-of-state health benefits that are very large and driving this decision for retirement of this infrastructure. So in terms of a summary, we have looked at improved air quality and human health in a systematic framework, rather than having these discussed just as co-benefits from a climate change policy. This is something that had been rarely considered when designing or implementing climate policies and assessing their implications. We determined the best locations for replacing power plants with new wind, solar, with storage or natural gas to meet an exogenous CO2 reduction target across the United States of 30%. We developed and employed a capacity expansion model coupled with integrated assessment models for climate and health damages, and compared portfolios for the benefits for climate and alone with both health plus climate. I'll note that all of this modeling and data is really open source, and would love to see other modelers exploring other alternative scenarios and expanding on this work. The model estimates county level damages and account for uncertainty by using a range of air quality models, so AP3, EASIUR, and InMAP, and concentration response functions. And we find that reducing CO2 by 30% can yield between $21 and $68 billion in annual health benefits from reduced air pollution, with an additional between 9 and 36 billion possible when co-optimizing for climate and health benefits together. And we do find that total health benefits may equal or exceed climate benefits across a wide range of modeling assumptions. So treating this as an add-on rather than explicitly may be a mistake. And finally, additional benefits accrue from prioritizing emissions reductions in counties with high population exposure. Our results do demonstrate the value of considering the health and climate policy design and the need for interstate cooperation when thinking about energy and climate policies for these next decades as a way to achieve equitable outcomes. And I'll then end with that. Thank you so much for your attention. I hope the sound and image was okay on your end.
Thank you very much, Professor Azevedo. That was wonderful. And we only had a few blips in the sound, so it was not a problem at all. So I'd like to move to have some questions. Please raise your hand and I will call on those of you. I do see there's one question in the chat that came in. And that asks, I understand the burning of coal has the biggest negative effect, but did your study look at fugitive emissions of methane and the impact on ground level ozone? Big problem in gas producing states. I realize you did mention some inclusion of fugitive methane, but perhaps you can speak to the, I guess it's asking about the production of natural gas rather than the combustion.
Thank you for raising this. Yeah, the aspects relate to methane, as I explained, we did account for fugitive emissions and the conversion of those into CO2 equivalent factors. And so that's accounted for when we produce the overall net damages across scenarios. We didn't look at interactions with ground level ozone. That's a really good point. I'm happy to follow up separately.
Okay, so I didn't follow exactly who raised their hands first, but we'll start with Tanner and then move to Farhana and Chinook. So Tanner, please go ahead.
Thank you for presenting today. This actually hits really close to home. I'm from Beaver County. If you spent some time in Carnegie Mellon, I actually have a map of, that's a map of Pittsburgh right there, because I am a big fan of my hometown area. My question kind of relies on, so I grew up actually hearing like how Western PA is, yeah, we produce a lot of pollution, I guess, and it shows, you know, a lot of your data shows that, but we had to blame Ohio, Indiana, and so and it's actually very interesting to see that in your data, because I've always heard that anecdotally, which is weird to think that anybody where I'm from listens to science. And so what I guess the real question is, what was kind of the previous, like what were the predecessor studies? Because it's just weird to me to think that like I've heard this my whole life, but no one was obviously like presented papers to like anywhere I know. So I just didn't know if there was any sort of, what was the early work that was done in this region, or I guess in general, like when did this become a thing? If that's a very broad question.
So yeah, thanks for your question. So I would say that the sort of mapping specific to the power sector that shows this sort of where emissions are produced, where they are suffered. I do think our mapping was amongst the first ones doing that, but I'll refer you to the work. There is some really interesting work by Nick Mueller, one of the co-authors at Carnegie Mellon. And he had done quite a few previous papers that looked at all sorts of emissions and running the model to understand their dispersion from location to location. He may have had, I'm not sure about that, so happy to follow up offline in trying to identify that. We actually have key matrices that look where is the source of emissions and receptor by state. So who are important, where is the damage being produced versus received. Some of his earlier work may have done that in the broad context of energy systems, not sure whether specifying the electricity sector alone. But he would be like the first go-to stream of research that I would look at. There was also some very early work by Lester Lavels at Carnegie Mellon, looking specifically at those states and the contributions of air pollution from coal power plants and monetizing those in terms of health damages. So that may be another source of information. Yeah.
Thank
Hope
you.
this helps. Yeah, but I would suggest looking as a starting point also to the supplemental document that we have produced that shows those trade-offs in several other ways, like the matrix that I just mentioned. Yeah.
Thank you.
Thank you, Dr. Azevedo, for presenting today and representing your extensive work on how climate change impact can, regulate policies related to environment and human toxicity. So, so you have presented your work in a way how it can influence policy regarding, so that no further damage can be made or something like that. Have you also considered presenting your research in a paper in a way that also influences, like rectifying the damage that has already been made, or because health damage, because many people have already been affected by the environmental effects of several industries, for example, transportation or energy. So have you also considered that? And there's also a second part of that, like, have you also noticed that is there an actual policy that's in making, or that that has already been implemented, that and your research has contributed to that? Thank you.
Yeah, so a lot of great questions to unpack. I'll start by saying that the aim of the research is not to influence policy. It is to outline the implications of different policy designs. So I'm not the policymaker. So this is outlining the implications that decisions may have, so that decision makers can make informed decisions as they go about thinking about these problems. That's a great point that you bring, meaning one could certainly look at the health damages that have been historically produced and understanding how those change over time. It turns out that we did a portion of that. So in a paper in PNAS, we looked at the emissions from the national emissions inventory across all sources and looked at how those have related to the value added from different industries and the economy. So really understanding, okay, are the externalities that each sector is imposing in terms of just health damages, not even considering climate change, larger than the value that they are providing to the economy at the margin? And if so, that raises questions about the efficiency of those productive processes and potential justification for regulatory action given that. So happy to share those materials, but we did look at different sectors of the economy, different years, and how that has been changing over time. We didn't look very far back, so some of these things are also limited by the availability of data and how the structure of the economy has changed. But I'll send that your way. So that's a PNAS paper from two or 3 years ago. Yeah.
Thank you so much.
Chinook, please go ahead.
Yeah, hi. My name is Chinook, and I'm recent graduate from Energy Graduate Group, and now I'm working as a postdoc at Policy Institute at UC Davis. And actually, I have one question about the social impact assessment. So it seems like you consider health damage as social impacts in your analysis, but as I know, the labor conditions are one of the major component of that social impact assessment. For example, if we are replacing the coal power plants to natural gas power plant or solar or wind electricity, then for example, the most exposed population will be who live near the coal power plant, and highly possible they are the workers at the coal power plant. So if we are kind of closing down the coal power plants and replacing with other power plants, it may affect the labor conditions of those communities who maybe work at the coal power plant, also as well as impacted by the coal power plant. So how this kind of labor conditions or labor conditions and the air quality issues related to those coal power plant can be included in your analysis or social impact assessment. Can I hear about your opinion or your kind of approach to that kind of issues?
Yeah, so those specific impacts are not considered in the type of modeling that I presented today, or they are to the extent that the workers are living in the counties that are affected. So since we account for the county population, but not specifically on the increased exposure that they may have for factors between the power plant production. There is a lot of work more related with exposure, both mostly indoor versus outdoor level of exposure that could contribute to what you're looking at that we didn't include explicitly here. And the other factor that you mentioned in terms of labor would be actual displacement or replacement of labor from one type of plant to another. We looked at that in another paper in the context of the Marcellus Shale jobs and implications, also looking at some of the EJ aspects related to that and whether the jobs were really temporary or long-lasting as you'd have these sorts of transitions, but much more needs to be done. So the short answer is it was out of scope for what we looked at in this paper. It may be an important dimension of distributional effects to consider in the future. We have at least one case study that I'm happy to share, but I'm not prepared to say more on the direction that even these things could take when included all across the board and for different counties.
Thank you.
All right, we'll have Christy, please go ahead and ask, and then we'll move to some questions in the chat.
Yeah, thank you for speaking to us today. I was wondering if you looked at the deaths related to air pollution by race by geographic areas as opposed to the US. I asked because I know that a lot of Asian and Latino communities are actually in the West, which had less deaths overall. I was just curious if this was different, the results were different, say in the South or in the Midwest.
They are, that's a very good question. And I did mention it, but very briefly in the slides, we did look at this for different RTOs and different regions, and the underlying demographics is different. So we do see different things. So again, happy to share, but in the paper, in the SI, we do similar plots with premature mortality by income and race and ethnicity groups for each of the regions separately. And each one has a different story to tell. That's for sure. So that should be that could be much better described. I didn't include that in the context of this particular seminar, but they are different.
Thanks. Okay, I see a question in the chat from Daniel, who asks, do you feel the monetization of all benefits, social costs of carbon, health, etc., as a standard practice for climate change mitigation modeling can make it harder to represent the actual impacts on social groups? For example, disadvantaged communities, for instance, health damages as dollars from community versus health damages as percent of community affected.
This is such a good and loaded question. So I must say that I'll be the sort of first critic to what is the social cost of carbon and the whole implications that we do with a value of a statistical life. So let me disentangle first on one, are they useful versus are they not useful? And I'll tend to argue that they are still very useful to have a standard approach to compare and contrast against the allocation of scarce resources for different potential policies. So in that regard, that may be useful information in still having those values. the second point is, are they precise and can we rely on that as ground truth? No, we can't, right? So those are embedded on a lot of assumptions. And if we're using both the social cost of carbon as well as value of statistical life for these decisions, my take and suggestion as a modeler and researcher is let's use a wide range of assumptions and try to understand where would the ultimate decisions that we're trying to make flip or change, and they're pushing those scenarios. Third, should we show it in terms of premature mortality only versus dollar values? I think that really depends on the question that we're trying to address. So as you may have noted in the first paper, we're showing everything just in terms of premature mortality numbers, and we didn't convert to dollar values because we're just contrasting premature mortality from air pollution across locations. Now, when we start trying to incorporate both the implications on climate change and health damages together in a common framework, we could keep those separate, but at some point you're doing implicit or explicit comparisons between action on climate change and global damages in the long-term and not so long-term future versus air pollution damages that are more local. So it's still helpful, in my view, to have a framework to compare the two. But being very cognizant that there's a load of assumptions that comes with it, and that those are not just, yeah, I'll leave it at that.